It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we introduced the recurrent neural network, the RNN. We celebrated its revolutionary idea, a network with a loop. This feedback loop allows the output from one step to be fed back into the network as an input for the next step, creating a hidden state that acts as the network's memory. This design we saw unlocks the ability to process sequences, to understand that the order of data matters. A simple RNN can look at the word the, and based on its memory, know that cat is a more likely next word than car. This was our first step into models that can handle language. But as is so often the case in science and engineering, this first brilliant solution came with a profound, practical, and deeply problematic flaw. The memory we celebrated in that simple RNN, it's incredibly short-lived. It's more like a fleeting impression than a robust recollection. Think about the last great book you read. The meaning of the final chapter doesn't just depend on the sentence before it. It depends on a character's choice in Chapter 1, a promise made in Chapter 5, a subtle clue from halfway through. Our minds are masters of context, weaving a thread of memory through hundreds of pages. Now, how do we teach a machine to do that? How can an artificial intelligence remember a crucial detail from the beginning of a long sequence to make sense of the end? For the longest time, this was one of the biggest hurdles in AI. These early neural networks, for all their pattern-matching prowess, had a form of digital amnesia. They were brilliant at understanding the immediate, but the past was a blur, a forgotten whisper. Today, we are going to tell the story of the architectural breakthrough that gave machines a reliable long-term memory. We're going inside the ingenious design of the Long Short-Term Memory Network, or LSTM. We'll see this with two examples. First, the clouds are in the most humans, and even a simple RNN would easily predict sky. The necessary context clouds appeared just a few words ago. The RNN's short-term memory is sufficient. Now consider this passage. I was born and raised in France. I spent my childhood in Paris, attending local schools and speaking the language with my family every day. After university, I moved to Berlin, but I still travel back to Lyon to visit relatives. Because of this, I speak fluent. The obvious answer is French. But for a simple RNN, this task is nearly impossible. The key piece of context, France, appeared dozens of words ago. By the time the network reaches the end of the passage, its memory of France has been completely washed away, overwritten by all the intermediate words like Paris, schools, Berlin, and Lyon. The network seemed to forget anything that happened more than a few steps in the past. This isn't a minor bug. It's a fundamental failure. It's the long-term dependency problem, and it rendered simple RNNs almost useless for real-world tasks. This catastrophic failure has a name: the vanishing gradient problem. To understand it, we need to recall episode 13, where we learned about gradient descent and backpropagation. This is how these networks learn. The process is about correcting errors. After the network makes a prediction, it compares its guess to the right answer and calculates an error or loss. Backpropagation is the process of sending a correction signal, called a gradient, backwards through the network, telling each connection how to adjust itself to make a better prediction next time. For RNNs, this is called backpropagation through time, or BPTT. The error signal, that big wrong, has to propagate backward through time, all the way from the last word back to the first. Here's where the analogies come in. Imagine the unrolled RNN is a long line of people, and you're at the end. You see the final mistake and need to send a correction all the way back to the person at the start of the line. This correction is the gradient. In a simple RNN, this process is like a game of telephone or whispers. You whisper the correction to the person in front of you, who whispers it to the person in front of them, and so on. With each whisper, the message gets a little quieter, a little less distinct. By the time the message reaches the start of the line, it's just a faint, unintelligible murmur. The gradient has vanished. Another way to visualize this is with a bucket brigade trying to put out a fire. The water is the error signal, but each person in the line spills a little bit of water as they pass the bucket. By the time the bucket reaches the fire at the end of the line, it's nearly empty. The people at the start of the line, representing the earliest layers of the network that process the beginning of a sequence, get no water, so they get no signal. They never learn how to pass the bucket more effectively. The technical reason for this spilling is rooted in mathematics. During backpropagation, this gradient signal is repeatedly multiplied by the derivatives of the network's activation functions, often functions like tanh, the hyperbolic tangent we met in episode 14. Here is the fatal flaw. The derivative of the tanh function is always a number less than or equal to 1, always. And what happens when you multiply a long chain of numbers that are all less than 1? Imagine you start with a strong error signal, a 1.0. After one step back, you multiply by, say, 0.5, your signal is 0.5. After the next step, 0.25, then 0.125, then 0.0625. Do this 20 times and your strong wrong signal of 1.0 has become 0.000009. It has become mathematically nothing. The consequence is devastating. The network's early layers, the ones that saw the beginning of the sentence, France, receive a gradient so close to 0 that they effectively stop learning. The network simply cannot connect a cause at the start of a sequence with an effect at the end. This leads to a common misconception. People often think vanishing gradient just means training is slow. This is dangerously incorrect. It doesn't mean training is slow. It means training fails. It means the network cannot learn long-term dependencies. Period. It's not a performance issue, it's a capability barrier. This wasn't just a simple bug. It was a fundamental mathematical consequence of the RNN's design. When you unroll an RNN through time, you're creating a very deep computational graph. The learning process requires multiplying a series of matrices, one for each time step. This is mathematically equivalent to raising a matrix to a high power. If the dominant values in that matrix are less than 1, the result vanishes. It's also worth noting that the opposite can happen. If the repeated multiplications involve numbers greater than 1, the signal can grow exponentially until it's deafeningly loud and nonsensical. This is the exploding gradient problem, which makes the network's training completely unstable. This is actually the easier problem to solve. We can use a simple brute force technique called gradient clipping. If the gradient gets bigger than, say, 5.0, we just clip it and set it back to 5.0. But vanishing gradients, that's harder. You can't clip a number to make it bigger. The signal is just gone. The very mechanism that gave the RNN its memory, the simple, elegant, recurrent loop, was the same mechanism that made that memory so fragile and impossible to train. The field had hit a wall. The solution came in 1997 from two researchers named Sepp Hochreiter and Jürgen Schmidhuber. In their seminal paper, they introduced a new kind of recurrent network architecture, the long short-term memory, or LSTM. They weren't just tweaking the existing model, they were directly confronting what they saw as the fundamental deep learning problem of decaying error signals. Their goal was audacious: to design a network cell where information and, crucially, the learning signal, the gradient, could flow over long durations without degradation. The conceptual breakthrough of the LSTM is the introduction of a separate, dedicated information pathway called the cell state. This is the absolute heart of the LSTM's design. The best way to think about it is with an analogy. Imagine the standard RNN is a single busy production line. The cell state in an LSTM is like a dedicated express conveyor belt running parallel to that main line. Information can be placed on this conveyor belt at any point, and it will travel all the way down the sequence with minimal interference. This design directly attacks the vanishing gradient problem. The conveyor belt, the cell state, is engineered to have only very simple, linear interactions. This means information can flow along it almost unchanged. In the original paper, this was called the constant error carousel, a mechanism specifically designed to let the error signal flow backwards through time without vanishing. This separation of concerns is a profound design choice. A simple RNN conflates two critical jobs into its single hidden state. It's supposed to carry long-term context from the past and produce a useful output for the current time step. This creates an impossible trade-off. To be useful for the current output, the state has to change. But every time it changes, it risks corrupting the very long-term information it's supposed to be preserving. The LSTM architecture explicitly separates these roles. First, the cell state, which we'll call CSUB, is the long-term memory conveyor belt, optimized for preservation. Second, the hidden state, which we'll call HSUT, still exists, but now it acts as the short-term working memory, a filtered processed version of the cell state that's used to make the current prediction. The name itself, long short-term memory, perfectly reflects this dual system design. But here's the final piece of brilliance. The LSTM doesn't just have this memory highway, it has a set of intelligent controllers, called gates, that carefully regulate what information gets onto the belt, what gets taken off, and what gets read from it. This is the key to its power and flexibility. So, let's step inside a single LSTM cell and meet these gatekeepers. It's important to remember that these gates aren't physical things. They are in fact just small specialized neural networks themselves, typically a layer with a sigmoid activation function. As we learned in episode 14, the sigmoid function is perfect for this. It squishes any number into a range between 0 and 1. This output acts like a dial or a filter. A 0 means let nothing through, block everything. A 1 means let everything through, open the gate completely. And a value like 0.6 means let 60% of the information pass. There are 3 of these gates, and they work in a precise coordinated sequence to manage the cell state conveyor belt. At the beginning of a time step t, our LSTM cell receives 3 pieces of information. The new input XSUT, the previous short-term hidden state HSUBT-1, and the previous long-term cell state CSUB-1. Here is the process that happens inside the cell. First, the network must decide what information is no longer needed. This is the job of the forget gate. Its purpose is to look at the old long-term memory stored on the cell state conveyor belt and selectively throw parts of it away. Let's use an analogy. Imagine the forget gate is a contextual cleaner reading a story. The first sentence is, "The cat sat on the mat." The cleaner makes a note in its memory. Subject is singular. Then it reads the next sentence, "The dogs played in the yard." The cleaner, seeing the new subject, dogs, immediately knows that its previous note about the subject being singular is now outdated and irrelevant. The forget gate learns, based on the new input, dogs, to turn the dial for the subject number memory slot to 0, effectively erasing that specific piece of old information to make way for new information. Mechanically, the forget gate looks at the new input XSUT and the previous short-term memory HSUBT-1. Based on this, it produces a 0 to 1 filter for every single number in the old cell state. This filter is then multiplied with the old cell state, zeroing out the parts that are no longer relevant. The ability to selectively forget is just as important as the ability to remember. Next, once we've made room by forgetting old information, the network must decide what new information to store on our conveyor belt. This is handled by the input gate, and it's a clever two-part process. You can think of this as a two-person team, a diligent note-taker and a strict editor. First, the note-taker, which is a layer with a tanh activation function, listens to the new input, the dogs played, and the previous context. It scribbles down all the potential new memories. It might create a list of candidate notes. Subject equals dogs, number equals plural, action equals played. This is our candidate vector, C tilde. Simultaneously, the editor, the sigmoid input gate itself, also looks at the new input and context and decides which of these notes are actually important enough to add to the permanent record. It might decide that subject and number are crucial for grammar down the line, so it outputs a 1 for them. This 0 to 1 filter from the editor is multiplied by the notes from the note-taker, approving only the important ones. The third step is simple arithmetic, updating the cell state. We take the old conveyor belt, CSUB-1, and do two things to it. First, we multiply it by the forget gates filter from the first step. This is where we threw off the old subject is singular note. Second, we add the new approved information from the input gate from the second step. This is where we place the new number equals plural note onto the belt. The equation is literally the new cell state equals the old cell state times the forget gate, plus the new candidate info times the input gate. Or, in mathematical notation, CSUB equals CSUB-1 times FSUT. That's the forget gate plus C tilde sut times ISUT. That's the input gate. Our conveyor belt, the new cell state CSUB, now rolls along to the next time step. It now contains number equals plural, which it added, and context France, which it kept from 20 steps ago. The France information has survived another time step totally unharmed. The final step is to decide what the cell's output for this specific time step should be. This output is the new hidden state, HSUT. It will be used to make an immediate prediction and will be passed along as the short-term context for the next LSTM cell. This is the job of the output gate. A good analogy here is a press secretary. The cell state, our conveyor belt, is like a president's entire library of knowledge, a vast collection of long-term memories. The output gate is the press secretary. When the network needs to make a prediction, the press secretary doesn't just dump the entire library of information on the public. That would be overwhelming and unhelpful. Instead, the press secretary carefully reviews the library. The updated cell state CSUB considers the current context, and then crafts a specific, relevant, and concise statement to release to the public. For example, if the network is trying to predict the next word and it needs to be a verb, the press secretary might look at the cell state, see the note that the subject is plural, and decide to output only that specific piece of information. This allows the wider network to choose the correctly conjugated verb, like play instead of plays. This entire gating mechanism is a form of learned dynamic attention. The choice of activation functions is deliberate. The gates use the sigmoid function because its 0 to 1 output is perfect for a controller or a filter. It represents a proportion. The layers that create the actual content for the memory, the note-taker, use the tanh function because its -1 to +1 output is zero-centered and can represent a wider range of values. This systematic separation of duties, gating versus content, is fundamental to the LSTM's stability and power. So, let's explicitly revisit the vanishing gradient problem. How did this complex contraption of gates and belts actually solve it? The answer lies in the cell state update. The equation was, the new cell state Kasub equals the old cell state Kasub minus 1 times the forget gate fsut plus the new information. Look at that first term. The relationship between the new cell state and the old cell state is incredibly simple. It's just a direct element-wise multiplication by the forget gate. Now think about backpropagation through time. The error signal flows backward, from Kasub to Kasub minus 1. As it flows backward, the chain rule says it must be multiplied by the derivative of that operation. Unlike the tanh function in the simple RNN, which always had a derivative less than 1, the gradient here is just multiplied by the value of the forget gate fsut. And the forget gate is learnable. This is the entire, breathtakingly brilliant insight. The network can learn to control the gradient flow. If the network learns that context France is critically important for the French prediction, it will learn to set its forget gate fsut to 1.0 for that piece of information at every time step. What happens when the error signal flows backward through time, and at every single time step it gets multiplied by 1.0? It doesn't vanish. 1 times 1 times 1 times 1 is still 1. The LSTM creates a gradient superhighway. The cell state conveyor belt allows the error signal to flow backward, perfectly preserved, all the way from French back to France. The whisper down the lane is replaced by a high-fidelity, dedicated audio line. The network learns to keep the volume on that line at 100% for crucial information. At the same time, for irrelevant information, the network learns to set the forget gate to 0. The gradient for that information does vanish, which is what we want. The LSTM, through its gates, performs learned dynamic gradient flow control. This is what finally cracked the long-term dependency problem, and this breakthrough is what unlocked the AI revolution of the 2010s. But before we see its applications, we must discuss one crucial variant, because it's used in almost all high-performance systems. It's called a bidirectional LSTM. So far, we've only processed sequences in one direction, forward from beginning to end, but for many tasks, context from the future is just as important as context from the past. Think about translation. If you see the English word record, you have no idea how to translate it. Is it a vinyl record, the noun, or to record a video, the verb? The only way to know is to see the rest of the sentence. I'm going to record a song versus I'm going to buy a record. A standard LSTM, reading left to right, would be stuck. It has to make a decision about record before it has seen a song. A bidirectional LSTM solves this. It's elegantly simple. It's just two LSTMs. The first LSTM reads the sentence from left to right, forward. The second LSTM reads the same sentence from right to left, backward. At any given time step, say, at the word record, we now have two hidden states. 1. The hidden state from the forward LSTM, which contains the context I'm going to. 2. The hidden state from the backward LSTM, which contains the context a song. We simply concatenate, or stick together, these two hidden states. This combined vector now represents a complete understanding of that word, given its entire context, both past and future. This complete bidirectional context is then fed to the final output layer, which can now easily see the full picture. With this architecture, the LSTM broke through the wall that had stopped RNNs. It could learn dependencies across hundreds of time steps, and it quickly transitioned from an academic curiosity to the undisputed workhorse of sequence modeling. For nearly a decade, from the late 2000s to the late 2010s, if you had a problem involving sequential data, the LSTM was the default, state-of-the-art solution. Perhaps the most famous application was in machine translation. In 2016, Google announced a massive upgrade to its translation service, replacing its long-standing statistical methods with a new system called Google Neural Machine Translation, or GNMT. The core of this revolutionary system was a deep, stacked architecture of LSTMs. Specifically, it used what's called an encoder-decoder model, where both the encoder and the decoder were built from 8 layers of those bidirectional LSTMs we just discussed. LSTMs were perfect for this. The robust long-term memory, carried on that cell state, was essential for preserving the meaning of an entire sentence across long, grammatically complex structures, leading to a dramatic leap in translation quality. But the LSTM's impact was felt far beyond translation. In speech recognition, LSTMs became crucial for acoustic modeling, transcribing spoken language into text with unprecedented accuracy. For years, the voice assistant on your phone was likely powered by LSTMs. In sentiment analysis, LSTMs could read a long product review and understand how early phrases like, "At first I was skeptical," completely change the meaning of the final sentiment. "But now I absolutely love it." They captured nuances that simpler models, which might just count positive and negative words, would completely miss. In time series forecasting, LSTMs became a go-to tool in finance for predicting stock prices, in meteorology for weather forecasting, and in retail for demand forecasting. Their ability to remember long-term seasonal patterns while simultaneously reacting to short-term, volatile events was invaluable. They were even used for creative pursuits, like music and text generation, learning the complex, long-range structures in existing works to compose new melodies or write plausible paragraphs. As LSTMs grew in popularity, researchers experimented, leading to a number of variants. The most successful and enduring of these is the Gated Recurrent Unit, or GRU, proposed in 2014. The GRU is essentially a simplified version of the LSTM. It makes 2 clever changes. First, it combines the forget and input gates into a single update gate. Second, it merges the separate cell state and hidden state into one unified state. The result is a model with only 2 gates instead of 3, and consequently, fewer parameters to train. This leads to a clear trade-off. GRUs are computationally cheaper and often faster to train. For many tasks, especially those with smaller datasets, GRUs can perform on par with LSTMs, offering a more efficient alternative. However, for problems that require the memorization of extremely long and complex dependencies, the LSTM, with its dedicated cell state and finer-grained control, may still have an edge. The reign of the LSTM, however, was not to last forever. While revolutionary, it has a fundamental architectural bottleneck: its sequential nature. To process the 10th word in a sentence, an LSTM must first process the first 9, one after the other. This makes it impossible to parallelize the computation within a single sequence, which is a major drawback on modern hardware like GPUs that excel at doing many things at once. In 2017, a new architecture arrived that would change the landscape of AI: the transformer, which we will dedicate an entire future episode to. Transformers did away with recurrence entirely. Instead, they use a mechanism called self-attention to process all words in a sequence simultaneously, in parallel. This allowed them to be trained on vastly larger datasets and led to the large language models that dominate AI today. So, with the rise of the transformer, are LSTMs dead? The answer is a definitive no. While they are no longer the default choice for large-scale language modeling, LSTMs remain powerful and highly relevant on smaller or noisy datasets, where a massive transformer can overfit. LSTMs often show more robust performance. For many time series forecasting tasks, where the strict sequential order of events is paramount, LSTMs remain a highly effective tool. But perhaps the LSTM's most important legacy is conceptual. The evolution from the simple RNN to the gated LSTM to the parallel transformer isn't just a story of replacement. It's a story of abstracting and improving the very concept of context. The simple RNN had a fragile, implicit sense of context. The LSTM introduced explicit, gated control, proving the immense value of learning to manage context dynamically. The transformer then took that idea and parallelized it. The LSTM was the critical, foundational intermediate step. It taught the field how to think about memory in neural networks, paving the intellectual path that led to the attention mechanism and beyond. Today, we've journeyed from the simple but amnesiac RNN, plagued by the mathematical curse of the vanishing gradient, to the brilliant solution proposed by Hochreiter and Schmidhuber. We went inside the LSTM cell and saw how its elegant conveyor belt cell state and its three gatekeepers, forget, input, and output, provided a robust architecture for memory. The true legacy of the long short-term memory network is the idea that memory in an AI shouldn't be a passive byproduct of its structure, but an active, dynamic, and managed process. The LSTM taught us that for a machine to truly understand a sequence, it needs to learn not just what to remember, but also, crucially, what to forget. We have now explored how AI sees the world with convolutional neural networks, and how it remembers the past with LSTMs. We have, in effect, been building the sophisticated minds of artificial intelligence. But what happens when we take these powerful brains and install them inside a physical body? What happens when an AI has to contend not with clean digital data, but with the messy, unpredictable, and physics-bound physical world? Next time, in episode 19, we step out of the abstract and into the concrete. We will explore the world of robotics and embodied AI. We'll examine the unique and immense challenges of teaching an AI to grasp an object, to walk, and to navigate the three-dimensional space that we humans take for granted.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.